Hello everyone. In this video we are going to talk about multivariate centralized motion control. So as the name says, this time the goal is not to say that the robot does not move fast, the gearbox ratios are large. We can assume that each joint can move kind of independently from the others, and the effect of others is a small disturbance. This time we consider the general case, not any limiting assumptions. The robot can move very fast or very slow, or can have all sorts of motion. The motion of each joint does depend on the other joints. They are all affecting each other. The couplings are not small. So now we are going to do a centralized multivariate control, right? So we consider everything together as a vector. Now, there are some topics under the field of controls, adaptive control and robust control, that come here and show themselves when they show themselves like adaptive control or robust when the parameters of the system cannot be really estimated accurately, or they are not known to a very high degree of accuracy, right? So when we say mass of link 1, mass of link 2, length of link 1 and 2, and so on, we are always assuming we know them very well. If we don't, then a lot of the computations that we do here, which are based on feedback linearization, will not do their job properly, and that's where you have to either do stuff like system identification and try to estimate those to a good degree of accuracy, or come up with other methods of control like adaptive or robust control, such that in adaptive control you try to estimate the parameters of the system at the same time that you control the system. In robust, you try to design such that to some degree of variation in the parameters, your system can maintain its performance. So here what we use is going to be a simple PD compensator plus feedback linearization. Okay, and we try to make all of the joints follow their desired values all at the same time, not individually. If you remember, the equation of motion for a robot is in general mq double dot plus c of q q dot times q dot plus g of q equals u. Here I have neglected the friction terms, but if we have the friction terms, we can just add them to this and make it like a modified C matrix. But here, as I said, we just assume that C here is mainly due to the centripetal and Coriolis accelerations. Again, if there is a viscous damping term, we can easily add it to the C matrix. If there is Coulomb friction, that's a separate story, because we cannot write it as in terms of Q dot. We have to write it in terms of sine of Q dot. So definitely here we are neglecting Coulomb friction. Now, what we do in this method is you have two layers of control, an inner loop and the outer loop. The goal of the inner loop is to cancel the nonlinearity of the system using what we call feedback linearization, which I mentioned in my previous video, but I'm going to re-emphasize on that. And then the outer layer will be simply like a PD controller plus some feed-forward term, right? So it's feed-forward plus PD feedback and some, as I said, feedback linear. So this is also very, very similar to what? To the method of computer torque that I mentioned in one of my previous videos. The only difference, as we will see, is this term that we calculate here for the inner loop is not based on the desired values all. It is based on the desired and some feedback. So it is really a feedback linearization here. But the idea is very, very similar to the computed torque. So what do we do here? We say, well, this is my equation of what? My motion. Here, this guy on the top. Now, What are some terms that make life very hard for me in terms of control? Those are what? Those are these two terms, the CQ dot and G of Q. If I didn't have them, then, or here, if I did not have them, then my equation will be similar to, not exactly, similar to a second order differential equation, linear, but in this case it's going to be nonlinear because this M matrix is not constant, it's a variable. But definitely my system is going to be a simple, like double integrating U dividing by M can give me my Q double dot or something very similar to that. But adding this C and G is what makes the control of system a lot harder. So what we do is we say, how about in this U, we try to estimate that G and C. So we say this U that we pass to the robot through the controller, right? Because this U is a control signal. How about we make this U to have the same C and G in it that we try to estimate, plus something else. If I do that, then definitely these terms would cancel each other, and I can get rid of those highly nonlinear terms, Coriolis terms, centripetal terms, and gravity. Right? Now, how can I get rid of the extra nonlinear term, which is M? Because so far, definitely, I could, by this method of, if I can calculate G and C in my controller, and if my estimations are accurate, yeah, I get rid of C and G. What about M? Because M is the other nonlinear term that I have. Say, well, how about I'll try to make this extra term that I have to be M times the desired acceleration, A of Q. If I do so, when I set these two to be equal, what's going to happen? What happens is I will get what? I will get M times Q double dot to be the same as M times AQ. And if M is a matrix that I can invert, if it's invertible, you will get what? If you multiply by M inverse from the left side, then you will get what? Q double dot to be equal to A of Q. And this is a nice second order system. And if the terms in AQ are linear, you will make yourself from a highly nonlinear second order system to a linear second order system, for which we can easily use the controllers that we use in a linear system. Like what? Like a PD controller or a PD plus feed-forward controller. So that's why you see the U signal is chosen the way it is. Two terms in it are to cancel the nonlinearities in robot. The other term, MAQ, also, that M and this M would be canceling. So the goal of this is to entirely cancel out all nonlinear terms. That's why we call it feedback linearization. So through this feedback term, we try to linearize the system. Now, if I look at this U, what terms does it have? G and C. How can I estimate G and C? For G, I need Q. For C, I need Q and Q dot. So definitely, if I want to calculate this guy, I need to have feedback terms in my controller from what? From Q and Q dot. So I need encoders and I need tachymeters to give me position and velocity feedback. Otherwise, it's impossible to what? To determine this C and G. The other thing is the formulas that we have calculated for C and G are the best knowledge of us from the robot. It doesn't mean they are exactly the same as the true robot parameters. They are our best knowledge, best model of the robot. So if it happens that the model that we have from the robot, this C is not perfectly accurate, or this G is not perfectly accurate, what's going to happen? the thing that's going to happen is the C that you calculate or the G that you calculate is not exactly the same C and G of the robot. So you will have something like C hat or what? G hat, and then you cannot simply cancel C and C hat. C hat is your estimate of C. That's where I mentioned what? Adaptive control or robust control. What happens if your estimate of these nonlinear terms are not identical to what the robot has? Can your robot still be this nice equation? Of course not. There will be some residual terms. Those residual terms might make your control completely useless, really. Render it useless, right? Or make it not give you the performance that you want. So that's the area of adaptive and robust control, which is way beyond the scope of this course at the moment. But in the future, one of my goals is to at least cover adaptive control or system ID in one of my future playlists. So until then, we assume that we know G and C very well, and these two terms will cancel. And also we assume that the M matrix is invertible, and we can get to Q double dot equal A of Q. So that's very good. That's what the inner loop does, cancel nonlinear term. Now, what about the outer loop? The outer loop goal is to define this A of Q such that the error in my system, and the error is what? The error is basically the difference between Q desired and Q. The goal of it is for the error, the limit of error, when t goes to infinity, which we call error steady state, to be what? 0. So if I can choose this AQ so that I have a 0 steady state error, or it converges to 0 asymptotically, as you can see here, that is the best thing that I can do. That is my job done. My outer loop is working. Now, how can I do that? Well, all I need to do is to choose my AQ to be what? A proportional term plus a derivative term. These two terms can come from your PD controller, and some feed-forward term from what? From the desired. This is the acceleration desired, the acceleration of the joint desire. If I add these, so this is your feed-forward. If I add these together, that makes life very easy for me. Why? Because take a look here. If I make this AQ, as I said, to be QD double dot plus K0, or you might call it KP if you want, doesn't matter, you might call it KP, that's the same thing, times error plus KD times error dot, what's going to happen? Well, now I'm going to bring this term to this side, and it's going to be QD double dot minus Q double dot, which is based on this definition. It is what? If you take 2 time derivatives, that's going to be error double dots. So what will you get? You will get error double dot plus KD times error dot plus KP times error equal to what? 0. And if error is due to one joint only, it's going to be exponential function. If it's also multivariate, again, it's going to be exponential function, but each and every one of the components. So in this case, your error of t is going to be whatever it was in the beginning times some exponential function with some speed like omega, negative omega times t, where omega is the root again of what? The characteristic equation here, which is s squared plus kds plus kp. If omega wants to be a root of that, then all you need to choose is for kd to be negative 2 omega and for kb to be omega squared, or positive 2 omega, I'm sorry. Kd to be positive 2 omega, so negative omega is a root. Correct? So that's all you need for a single degree of freedom. If the system is multi-degree of freedom, like almost all of the robots, then your KD and KP is still going to look like 2 omega and omega squared, but this time diagonal matrices. And that's exactly what you see here. So if you choose your proportional gain and your derivative gain to be like this, where omega determines the speed of convergence to zero, the faster the omega, the bigger the omega, the faster the error converges to zero, your system is faster. But we learned in all of the previous video, I cannot choose omega to be very, very large because that means big gains, and big gains in real world cannot be achieved. Very, very large gains. So definitely my choice of AQ, the way we did it here, will lead to convergence of error to zero. Correct? So now, as you can see, this outer loop controller takes the Q desired and then generates what in it? Generates QD double dot in it. Also, when it receives Q and receives Q dot, here it subtracts and generates what? Generates the error. And then once it has error, it can generate the KP times error and the KD times error dot. So the PD controller here, let me add it down here. This PD controller is inside this outer loop controller. Plus, of course, the double derivative of the feed-forward term. That's where the AQ is generated. You pass AQ to the inner loop, and the inner loop takes AQ multiplied by M matrix, add the Coriolis centripetal and gravity terms to it, generate the control signal here. You should be calling it U or tau, and passes U to the robot to give you what? Q. And the system should be well capable of what? Tracking really any kind of signal Q of D. The important thing that you see here, I used is, first of all, I did not assume that the robot does move slowly. It doesn't. The other thing, I did not assume that QD is constant. Here, your QD can be variable. So you can do what? You can do real tracking. It's not just set point tracking. You can track what? QD of T. Okay, so this algorithm can track a time varying trajectory, not just a constant trajectory. Okay, and has no limiting assumptions. So in general, this algorithm, multivariate centralized motion using feedback linearization, is a very strong method, extremely strong, because it removes lots of those limiting assumptions. The only holdback is this. Are my estimates of C and G accurate? If they are, then it's perfect. If there are errors between C and C hat and G hat, and they are not small, then this method will fade to work very, very fast. Okay, so if you want this method to work, you probably need to do some system identification or adaptive control plus regular control that we do right now to make sure it works. Okay. Before I go and talk about the same method but done in the task space, because all the control we have done here was in the joint space, I can also show you the equations for the task space. But before that, I want to show you an animation, or a simulation, I'm sorry. So here is Simulink. And again, this is the 2 degree of freedom planar arm. This is my robot, where you pass to it the U1 and U2, right? Or tau 1 and tau 2. Of course, the robot also needs the feedback from its own Q1, Q2, Q1 dot, and Q2 dot. And you might say, why? In order to generate the Coriolis centripetal terms and the gravity terms. So you need those. And this is the function in it that will generate basically for you the Q double dot terms. So this block that I have for you, in it, you generate this C terms, the G terms, you create the M term, and at the end of the day, you subtract U from the C and G, or CQ dot and G, and multiply it by M inverse to get what? Q2 dot, or you might call it Q double dot. Okay, so that's what that block does. It calculates for you what calculates Q double dot, right? So if I go back up here and if I want to calculate my accelerations right now, let me see. Q double dot is what? M inverse times U minus C of Q and Q dot times Q dot minus G of Q. That's exactly what I'm doing in this block. And then you double integrate the Q double dot with the initial conditions of Q1 dot and Q2 dot. Here I use 0 and Q1 0 and Q2 0. I assume that you start with 6 degrees for link 1 and for the 10 degrees for link 2. And my goal here is to go to 60 degrees for link 1 and then 45 degrees for link 2. So I'm still doing set point tracking, but that's the goal here. And this is my outer loop control, which generates the U's. It takes the Q's and Q dots as well as the AQ's, right? The two components of AQ, AQ1 and AQ2, and it generates U based on the formula we just had, MAQ plus CQ dot plus G. And then we have the, I guess this should be, the naming is wrong. So let me fix it. This is inner loop, this is outer loop. I know, that's okay. So this is the outer loop. And this guy is the inner loop. Correct? That's what we had over here. Outer loop and inner loop. And the outer loop, is, if you remember, is the goal of it is to have a PD term, which you can see here. First, the error is generated, so this signal is error, right? Because QD came in and Q came in. Subtract to get error, multiplied by KP, multiply the derivative of it by KD. So this is the feedback term, and then this is the double derivative of QD, so it's QD double dot, add them all together and get you what? A Q, and here I use multiplexers and demultiplexers to combine basically several signals into one signal, or the other way, one signal, decompose it into several signals. So this is the overall basically Simulink for me. Everything is set up. And if you look at my KP and KD, I chose the same formulas. If you remember, my KP is, or K0 is diagonal of omega squared. So here my omega is 4. That's why you see 16, 0, 0, 16. It's a diagonal matrix. And my KD is 8008, and that's because the diagonal elements on KD or K1 are 2 omegas. Here I chose omega of 4 for both of the links. Okay, so these are my matrices, and I guess now I'm ready to simulate the behavior of the system for a set point tracking. So let's go ahead and do that. And there we go. And here I pass to these oscilloscope blocks, Q1D versus Q1, and then Q2D versus Q2. So this is Q1. Let's double click and take a look at it. Whether your Q1 could reach the desired value of it, and you see it absolutely did. The blue is the desired, and the red is what? The actual. And you see I could well reach the final value within 2.5 seconds or so. And similarly for Q2. Also, as you can see, again, you see that I could, again, within 2.5 seconds or less, I could go from the initial value of it to the final value of it, which was like, I assume the final was 45 and the initial one was like 10 degrees or so. Okay, so you see, I could easily achieve the final values, and the behavior is perfectly critically damp, no oscillation, no overshoot or undershooting here. Okay, to demonstrate that it can do more than set point tracking, here I have changed the inputs from constant step function or just constant numbers to ramp functions. So this is a ramp with the slope of 1, this is a ramp with the slope of 1.2, right? And let's say they are increasing, the angles are increasing versus time, the desired angles. The only point here is I have changed a little bit inside the outer loop, and instead of using the double derivative block, I use these constant zeros because this derivative block in the beginning that the simulation starts is not going to do a great job when you do double derivative. When you do first derivative, it's okay out of a constant because it's a line. When you do first derivative of that, you will get what? You'll get a constant, and when you do another derivative you get 0, but because it is doing the derivative numerically, the 0 that you would get really out of the double derivative is not going to be as clean as these zeros. It's going to have spikes in it. So since I know the double derivatives, the double dot derivative for both of them is 0, instead of using double derivative I use two constants. This allows me to simulate without any problem. If I still use double derivative, it would stop the simulation very fast and say, hey, I could not move forward. So know the limitations of this derivative block. And here you can see, as I show you, this is, yeah, maybe 10 seconds is a little bit too long. Let me just simulate it for 3 seconds. The response time is relatively fast, and you see here the red is the actual and this one is the desired, and you see very fast it can catch up with it in about 1 second or so, and now they are moving together. And the same thing for Q2, as you can see it can well track the time varying output. Okay, so this method is really capable of tracking more than a simple constant number. You can do more advanced tracking. And here I made it even more complicated. I made my second desired signal to be a sine function instead of a ramp. So now this is much there is much more variation in the sine function. It's just one sine of t, and the double derivative of one sine of t is simply negative sine of t, or sine of t plus pi. That's what you see I have provided here. It's sine of t but plus pi. I gave a phase of pi to represent the double derivative of that sine function. Since we know ahead of time what kind of desired function we want in most of the applications, calculating the double derivative of that like this real offline is not a big deal. And here we go, we simulated for 5 seconds, and again you see your ramp function is very fast converging, as well as your sine function. You see, so it just took less than a second for the Q2 desired to Q2 to match the time varying Q2 desired, and if you just simulate it for a lot more time, you see that there is no problem. Look, you see? So it can well track that, and this one can well track the line. So this is the advantage of this method. Okay, and by the way, I will share this file that I just showed you. I will share it and provide the download link under the video description. So take a look at that. As I told you, we can derive these control equations, right, and formulas in the task space, because many times the trajectory is really specified in the task space, not in the workspace. So we know our x desired, not q desired, and x here is the end effector pose, which is the position and orientation. If we know the end effector position and orientation, and we want to design our control, inner and outer, in the task space, we can have it, although some people might say, well, if I know my x desired, then I use my inverse kinematics and I get my q desired, and then I use the same formulas that you showed me above. Yes, you can do that. That's an alternative, okay? Or I directly go with these formulas that you have over here. Okay, each one of them needs something. So I'll show you that each one of them needs some extra thing when everything is specified in the task space. If you go with the method I just mentioned, then in real time you have to do what? Inverse kinematics. Unless, as I told you, x desired is given to us way ahead of time, we know it, so we can apply in offline the inverse kinematics, get our q desired offline, and then yes, now in real time all we need is to come up with control signals. Okay, but this one needs extra computation of inverse kinematics, or the way I'm going to show you, you need the calculation of the time derivative of Jacobian. Anyways, either way you do it, you need some extra computation, but it's not really that hard. So what do we do here? Again, x is the end effector pose, and pose means position and orientation both. J is the analytic Jacobian here, so we assume that when we say pose, the pose is like what? Like the end effector position, R, and the end effector orientation, alpha, where alpha is the minimal orientation representation. So alpha is like Euler angles or something. It is not really a rotation matrix, okay? Or if you want, instead of R, you might show it with D or O or something. So this is the minimal representation of the end effector, where the time derivative of this, correct? The time derivative of x is what? This is the end effector velocity, which we in the past showed with xi. And this xi, if you remember, it is what? It is d of the end, or velocity of the end effector in the base, and omega, angular acceleration of the end effector in the base. And this is equal to analytic Jacobian times q dot. Again, why analytic Jacobian? Because here we are showing what? Minimal representation of the rotation. Okay, so don't forget about that. Okay, if that is the case, the equations in the joint space are still the same thing that they used to be. Now, how can we relate them to the workspace or task space? So I just showed you that x dot is equal to j times cube. So when I say j, means j sub a. And then I also need another time derivative. So from this I take another time derivative. And that becomes end effector acceleration is equal to j times q double dot plus j dot times q dot, because both j and q dot here have time derivatives. It's a product rule. If that is the case, I'm still going to choose my inner loop control law the same as it used to be. So the inner loop control law has no difference with respect to what? The previous case. I still choose u to be this, and when I combine these two together, as we did last time, when I combine them together, I will still get what? I will still get q double dot equals a of q. Okay, I still will get this. The only difference here is a of q, which is the outer loop control. How do we form it? Well, because q double dot is what? Look at here. If I want to find my q double dot from this relation, what is q double dot? If I want to find q double dot from that relation, it is going to be x double dot minus j dot q dot. So I took this term to the left hand side and then multiply both sides by inverse of j. correct? That should give me what? The Q double dot, that now I set it equal to A of Q. Sorry, J inverse. Good. So now what should I do? I say, well, I choose this AQ to be what? Also J inverse times something. Because if I do so, then this J inverse times something is equal to this J inverse times X double dot minus JQ double dot, JQ dot, J dot Q dot. Therefore, by comparing them, whatever I choose here is going to be the same as what? X double dot minus J dot Q dot. Correct? Now, what do I want to choose inside this? Well, I definitely do not want this term J dot Q dot to get on my way of a simple PD control. So definitely, whatever I include in here, I also include negative J dot Q dot in it. So these two terms would cancel. If I do that, now what is going to be the rest of it? Well, just like last time, I choose XD double dot and then plus the PD control, which is KP times XD minus X, or the error term, and then plus KD times XD dot minus X dot, the derivative term. Then this is going to be equal to that. When you bring X double dot to the left side, then you will get what? You will get this guy. Correct? And this is exactly the equation that we had last time, except it was in the Q, in terms of Q error. This time it is in terms of X error. So if I call this guy X error, or in your notation here, you see I have used X tilde, which is the same as X error. So if you call this guy X tilde, this one, then this guy is going to be X tilde dot, and this guy is going to be X tilde double dot. And again, it's going to be a second order linear differential equation for which the solution can be what? X tilde is whatever it was at the beginning times exponential of negative omega times t, as long as you choose KD to be diagonal of 2 omegas and KP to be diagonal of omega squared. That guarantees that the error in the workspace or task space X tilde goes to what? Goes to 0 as t goes to infinity. Right? So you see how I formed AQ. For AQ, I needed a J inverse behind it, so those two J inverses can be cancelled. And here I assume that the J inverse can be cancelled from both sides, so J definitely should be invertible. In other words, this does not work at singularities. And then inside of it, not only I need the feed forward term plus PD feedback term, I also need a what in it? A negative J dot Q dot to cancel the other J dot Q dot. That's why you will get this guy that you see down here. So hopefully it's clear why we chose AQ the way we did. Just to cancel out the terms from the left and right hand side and end up with this simple equation that everybody knows where it converges to. Okay, so this is the outer loop control. This is the inner loop. The inner loop is exactly the same as Q space. The outer loop is a little bit more involved. As I said, you need to calculate some extra term J dot as well as J inverse. These terms you get from what now? You get from feedback from the task space. So this X is the position of the end effector that you have to feedback from task space and X dot. And these are not always easy, because when I want Q, how do I get Q? I get it from encoders, right? When I want Q dot for a motor, I get it from the tachometers. So getting feedback for angular position and velocities are not too hard, but the question is, how would you measure the end effector position in the task space? Using what sensor? Or how would you measure the end effector velocities in the workspace? What do you do that? So that's why this task space control is a little bit harder, because getting real feedback about end effector pose and velocities using any sensor is not as simple as encoder and tachometers, and most of the time we get these from computer vision or other sensors like basically range sensors or anything like that, magnetic sensors, all sorts of different sensors. But definitely these are a lot harder and a lot more expensive to get feedback from X and X dot. Okay, so I'm showing you the difficulties in reality of applying any of these control algorithms. Okay, but you clearly saw that I could easily apply that in the joint space, and changing it to a task space of this model I provide you should not be the hardest thing in the world. So hopefully this video was useful to you, and I will see you in my next video. Thank you.